Hey you guys, let me try to explain what I was talking to you about yesterday. This was a project. I just took a little clipping of it from the project. I looked, the date was from 2001, and so we've been doing this for a little while. But in this project, we had Mario going through a semicircular turn. I know in my little drawing here it may not look like a perfect circle, but if you look at the numbers, it is. So this is a semicircle, and honestly I don't remember 19 years ago, but for some reason I put the y-axis this way and the x-axis this way, notice. So you guys, just the point is this: when you have your track, superimpose a coordinate system onto your track and then measure some things. Now you guys will have to know, and will know more than I will know, about how a car goes through this track. So in my case, I said, okay, Mario enters the curve at time t equals 0. And if this is the origin, and for whatever reason, this is x. So x is 840, y is 0. 1 second later, x has decreased, because notice, again, x is this direction. So x has come down to 789, y has increased to 287. And then x has gone down to 643, y has increased to 539.9, etc. So every 1 second, I was providing a position of Mario. Now I'd like you to imagine is a vector, we call it a position vector, a vector that originates at the origin and terminates at wherever Mario is. So it's not just a single static vector, but it's a whole series of vectors that change as time changes. So when time is 0, we would see this vector here. When time is 1, we'd see this vector here, etc. So what we're looking for is a vector valued function based on t. So as t changes, x and y position changes, so therefore the x component of the vector changes and the y component of the vector changes according to some function. And so f of t, just for the sake of this video, f of t is going to be the function that shows x as a function of t. I should have probably, to be more traditional, flipped these around, because usually when we make functions, we say x is a function of t. No, that's right. I don't know why I just went backwards there, but no, this is right. So the independent quantity is t, the dependent quantity is x. So when t is 0, x is 840. When t is 1, x is 789. When t is 2, x is 643, etc. Same thing with y. Y is a function of t. When t is 0, y is 0. When t is 1, y is 287.2, etc. So you guys will have to imagine a car going through your curve on your track, and based on your experiences, figure out where would the car be every 1 second, every half a second, however you want to do it. Okay, so that's what I did for this project. Is we pretended in the project there was some kind of a video taken, and we were able to advance the video frame by frame by frame, and each of these was a location of Mario every 1 second as we advanced the frame. All right, so our job now is to come up with this formula, this function that says as t increases from 0 to 9. So when t is 0, we want to output this vector such that x is 840 and y is 0. When t is 1, we want this thing to output the vector such that x is 789 and y is 287, etc. So we need to get these functions. X is a function of t and y is a function of t. Here's how we can do it. Let me jump over to Desmos. So in Desmos, what I've done here is entered in, I don't know why I don't have 0. What was 0? 0 was 840, wasn't it? So enter in the data into Desmos, and then maybe you know this about Desmos, but we can enter in a generic, whatever, linear function, quadratic function, whatever you want, and using this tilde notation, it will generate a regression model or a curve fit for this. And I want to use a sine or cosine. I'm going to tell you 2 reasons why, one at a time. The first reason why is just thinking about that curve, do you see that we've got the start, at least, of a sinusoidal wave? Every time we go through that curve, it's going to repeat that wave, repeat that wave, repeat that wave, just again focusing on the curve. And so the generic sinusoidal is A, the amplitude, times the sine of bx. And I don't know if you remember this from your trigonometry, but the coefficient on x determined the period of the wave. And then plus c gave us a horizontal, a phase shift. And then the plus d gave us a vertical shift. And so if you just put in exactly what I've typed here, and it's y1 and x1 because that's where the data is located, is in y1 and x1. And so we have an a value of about 840, a b value of about, let's just call it 0.35. I think I ended up saying d is negligible, 0.00. Let's just leave it off. And c is 1.57. And so notice it fits the data pretty darn well. Now what I did is adjusted it ever so much. So I said, hey, let's just call that 840, just for the sake of modeling, call that 840. Let's call the b 0.35, and let's leave off d, it's too small. And now watch this, c is 1.57. Now because I'm a geek, I know that 1.57 is pi over 2. If you phase shift by pi over 2 a sine wave, you get yourself a cosine wave. And so you might remember that a sine wave normally starts at 0 and does its thing. Well, if you shift it over pi over 2 units, you get a cosine wave. So I just removed the shift and called it cosine. So 840 cosine, and you can see that it's just as good as the actual regression with all the decimal place accuracy up here. Okay, so whatever model you like. Now this was, you'll see later, this was a semicircle. That's going to matter here in just a second, but let me first do the same thing for the g function. Remember, the g function was my y, or the j hat component of my vector. And so I again entered all the data, did a regression, and A is 840. Now the 840, the reason that's particular is I don't remember exactly the details of this project, but I scaled it so that the radius of the circle was 840 Mario units. Okay, you guys will have some specific measurements in feet or whatever, meters, whatever you want to use. B is again 0.35. I made C is practically 0. It's negligible. And I said, look, that D is pretty small too. Let's make it just 0. So I just made it 840 sine of 0.35t. Now you can see, let me turn on the data first. There was the data, more traditional sine wave, because notice we didn't have that shift. So we start at 0, 0, and we have at least a portion of the sine wave. And you'll notice that there's the curve fit in its fullness, and then here's the curve fit in my kind of truncated, abbreviated version, and you see that it is just about as good. All right, so now let's put it all together. So remember this thing over here. We now have these functions to model the position of Mario as a vector that terminates at that the components of that vector. And so the components would be whatever f of t is of I plus whatever g of t is j. Now in terms of Desmos, I can just plot g of t, f of t as an ordered pair. So I just, like, you can plot an ordered pair like 1, 2, 1, 3, and it'll plot that ordered pair 1, 3. So I can just plot the ordered pair g of t, f of t. I guess I have it backwards, don't I? And it will plot the points just like in this image. It'll show, you'll see in a minute, it'll show all those locations that Mario was as time increases from 0 to 9. Notice I made t increase from 0 to 9. Okay, so let me turn off everything else. And you will see, now the second thing I wanted you to know why sines and cosines kind of matter here is that when you put sines and cosines together, maybe you can imagine from a unit circle, cosine of theta is this length, and sine of theta is this length. And so when you put sine, cosine, comma, sine together, you do get a circle. Now remember that was an 840 by a radius of 840 circle. So I need to help you to see it. And I need to turn it on. Aha! There it is. Now remember in my PowerPoint, maybe I was just trying to mess with students in terms of coordinate systems are somewhat arbitrary. We have a convention that we do it a certain way, but maybe I was trying to break the mold a little bit. So I have the y-axis and the x-axis kind of flipped. So my semicircle's on its side in this view, but in Desmos it looks more normal, x-axis, y-axis, and so there's your semicircle. And so Mario is making this curve. And now that I have the vector valued function, we can do stuff with it. For instance, you can take the derivative to get the velocity vectors. So just take the derivative of those functions I. Take the derivative of that function j. Or you could get a second derivative and get an acceleration. And as you saw in that sheet, those velocity vectors should be tangent to the curve. The acceleration vectors should be pointing toward the center of the circle, like a centrifugal force kind of a thing. And so the dot product between those two vectors should be 0, all kinds of fun stuff like that. But anyway, I hope that at least gives you some help on how you can go about modeling this vector valued function, a little bit of insight into what a vector valued function is, so that you can move forward on your project. Hey, stay in touch. Let me know if I can help.